Since the dawn of humanity, we have gazed up at the night sky and wondered about our place in the cosmos. The twinkling stars, distant and unknown, have fueled countless stories, myths, and dreams. For millennia, they remained out of reach, points of light in an unfathomable void. Yet something within us yearned to explore, to venture beyond our world and touch the face of the infinite. Today, that yearning has evolved into a bold ambition: intergalactic travel. We dream of venturing beyond the familiar embrace of the Milky Way, of setting sail across the cosmic ocean to reach islands of stars billions of light-years away. It's a dream that pushes the very boundaries of our understanding, a challenge so immense that it forces us to confront the limits of our technology and the very nature of reality itself. But the dream is there, whispering to us from the depths of our collective imagination, urging us to reach for the impossible. Can we truly break free from the gravitational shackles of our galaxy and embark on such an audacious journey? What challenges await us in the gulf between galaxies, and what wonders might we uncover on the other side? These are the questions that drive us, the mysteries that beckon us forward on this incredible journey of exploration. Join me now as we delve into the science, the possibilities, and the profound implications of intergalactic travel. Together we'll explore the cosmos and discover just how far humanity's reach can extend. Before we can even contemplate intergalactic voyages, we must first grasp the staggering scale of the cosmos. Our solar system, a tiny oasis of life in the Milky Way galaxy, is but one of billions of such systems scattered across a vast stellar disk. The Milky Way itself, a swirling city of stars spanning 100,000 light-years across, is just one galaxy among trillions in the observable universe. To truly comprehend the challenge of intergalactic travel, consider our nearest galactic neighbor, Andromeda. Located a mere 2.5 million light-years away, Andromeda is a breathtaking spiral galaxy even larger than our own. This distance, while seemingly insurmountable, is actually relatively small on the cosmic scale. Even traveling at the speed of light, a physical impossibility for a spacecraft, it would take 2.5 million years to reach Andromeda. This means that even if we could somehow achieve light-speed travel, a one-way trip to Andromeda would take longer than the entire recorded history of human civilization. The vast distances between galaxies present a hurdle unlike any we've encountered before. Yet, understanding the sheer scale of the cosmos is not a deterrent, but an invitation. It's a call to expand our thinking, to push the boundaries of science and engineering, and to dare to dream of technologies that can conquer these unimaginable distances. The first step on this incredible journey lies in comprehending the vastness of the challenge. Only then can we begin to imagine the extraordinary solutions that will be required to overcome it. In 1905, Albert Einstein, through his theory of special relativity, presented a fundamental limit to our cosmic aspirations: the speed of light. This cosmic speed limit, approximately 299,792,458 meters per second, governs the very fabric of space-time. It dictates that nothing, no object with mass, can ever reach or exceed this speed. Imagine a spacecraft powered by the most advanced propulsion system we can conceive. As it accelerates, approaching the speed of light, strange things begin to happen. The spacecraft's mass increases, asymptotically approaching infinity as it gets closer and closer to the speed of light. This means that accelerating further requires ever-increasing amounts of energy, quickly reaching impossible levels. The implications are profound. Even if we could harness the energy of entire stars, we could never quite reach the speed of light, let alone surpass it. This cosmic speed limit presents a seemingly insurmountable barrier to our intergalactic ambitions. If we are bound by the laws of physics to travel at sublight speeds, then journeys to even the nearest galaxies would take millions of years. This realization could easily lead us to despair, to conclude that intergalactic travel is nothing more than a fantastical dream. However, within the very laws of physics that seem to constrain us, we may also find the seeds of extraordinary solutions. To break free from the chains of conventional propulsion, we must venture into the realm of the theoretical, to explore concepts that sound like science fiction, but are rooted in the elegant mathematics of theoretical physics. Section 4. Wormholes and warped space. Einstein's general theory of relativity describes gravity as the curvature of space-time, opening up possibilities for interstellar shortcuts, wormholes, and warp drives. Imagine a fold in spacetime, a shortcut connecting two distant points in the universe. This is the concept of a wormhole. By traversing this shortcut, a spacecraft could bypass vast distances and emerge far faster. However, wormholes remain highly theoretical and unproven. Another possibility is the warp drive, manipulating spacetime to create a warp bubble around a spacecraft. These concepts highlight that our understanding of the universe is constantly evolving. Section 5. The void between the stars. Let's assume for a moment that we can overcome the challenges of distance and develop propulsion systems capable of propelling us across the gulf between galaxies. We then face another daunting obstacle: the perilous nature of intergalactic space itself. Unlike the relatively bustling neighborhoods of star systems and galaxies, the intergalactic medium is a cold, dark, and unforgiving environment. Imagine the emptiest, coldest desert on Earth, then magnify that emptiness and coldness trillions of times over. That's a glimpse into the harsh realities of intergalactic space. The extreme cold, near absolute zero, poses significant challenges for spacecraft design and life support systems. The lack of matter, while simplifying navigation in some respects, also means there are no refueling stations, no convenient sources of resources. Any intergalactic spacecraft would need to be entirely self-sufficient, carrying all its fuel, supplies, and resources for a journey that could last millennia. Then there's the radiation. Without the protective shield of a star's magnetic field or a planet's atmosphere, intergalactic travelers would be bombarded by constant cosmic radiation, posing significant health risks to any living crew. This means that shielding technology would be paramount, requiring innovative materials and design solutions to protect both spacecraft and crew from the ravages of space. Overcoming these challenges would require a level of technological sophistication that dwarfs anything we currently possess. It would demand not only advances in propulsion and energy generation, but also in materials science, life support systems, and radiation shielding. Section 6. Powering the impossible. Intergalactic travel demands a radical rethinking of how we power spacecraft. Chemical rockets are inadequate for such a journey. Even nuclear fusion might not be enough. We need to think bigger. We need to tap into the raw power of stars. One concept is the Dyson sphere, a megastructure that captures a star's energy. Imagine a vast sphere surrounding the sun, acting as a gigantic solar panel, enough to power entire civilizations. Another concept is the star motor, using a star's energy for propulsion. These ideas highlight an important point. To achieve the impossible, we need bold ideas. Intergalactic travel demands radical solutions, pushing the boundaries of science and imagination. Questions.